Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler and today we'll be doing unit number 10, lesson number 9, on the volume of pyramids and cones. Alright, so in the last lesson we looked at the idea of volume, the idea of measuring the amount of three-dimensional space that fits inside of a three-dimensional object, right? Whether you're measuring it with gallons or cubic inches, you're using some basis and then figuring out how many of these things fit inside. Today, we're going to look at the volume of pyramids and cones, all right? So let's kind of jump right into it right away, and then let's recall some things from the last lesson, right? The volume of a prism, right? A prism can be found by simply multiplying the area of its base by its height. And it doesn't really matter whether it's a prism that looks like this or a prism that looks like this that's more slanted. If I can, some way, figure out the area of this pentagon and multiply it by this height, then that gives me the volume. The key, of course, with prisms, and cylinders also fit into this, is that the cross sections are always the same. So if I sliced this particular pentagon horizontally, I would find, this prism horizontally, I would find a pentagon that was identical to the top and the bottom. All right, same thing over here. But pyramids and cones, they're a little bit different, right? So a pyramid is a solid with one face that's a polygon of any type, and then all other faces are triangles that meet at a common vertex, right? And again, you could have a pyramid that's sitting on its base, or you can have a pyramid that's kind of turned. Either way, the key is, that base is going to be some polygon. Here it's a quadrilateral, here it's a hexagon, and then there's going to be an apex, and all other faces are going to meet up at that apex. So what we're going to look at today is how do we calculate the volume of those kind of pyramids. Now, the volume formula for a pyramid and likewise a cone are not hard formulas, all right? But there's something about them that's a little strange, and we're going to get at that in the first exercise. So let's take a look at it. Exercise number 1, consider a cube that has side lengths of 2 centimeters each. All right, so this big cube here. The center of the cube is located and segments are drawn to each of the 8 vertices of the cube. This created the pyramid whose volume we're going to explore, all right? So we're going to explore the volume of this particular pyramid, all right? Very simple, all right? Letter A, real easy. What is the volume of the overall cube? Take 30 seconds, pause the video, and go ahead and calculate that. All right, well, the volume of a cube is a prism, right? And the volume of any prism will be the area of the base, right, times the height. So the volume of a cube, in this case, is 2 times 2. That's really the area of the base, right, times the height, 2. All right, and that will be 8 cubic, not cubic inches. How about cubic centimeters? All right, very, very simple, 8 cubic centimeters. Now, letter B, how many of these pyramids would fit into the original cube, right? So how many of these could I fit into that cube, all right? Why? And then I'd like you to use that answer to actually figure out the volume of that pyramid. So take a moment to do that. All right, well, it's pretty easy. 6 will fit into the cube because we could create one a pyramid for each of the 6 faces. There's my red showing up again. Each of the 6 faces. All right, I want you to make sure you understand that, right? So I created this particular one, but of course I could also create one off of this face. I could create one off of the face at the top, the one at the face here, the one at the face at the back. Every cube's got 6 faces, and for each one of those, I could create one of these pyramids and kind of shove it in as kind of a puzzle piece, if you will. Now, that's awesome. because that allows me to directly figure out what the volume of this particular pyramid is. The volume of that pyramid must be 1/6 of the volume of the overall cube. So that would be 8/6 or 4/3 cubic centimeters. All right? So this particular pyramid has a volume of 4/3. All right, great. Now keep in mind that it's got a base that's a square 2 by 2, and it's got a height of only 1 centimeter, right? Because it only comes up halfway in this overall cube. Now, we can actually put this pyramid inside of a prism that's a little bit shorter, right? And in fact, this prism that I've got right here is basically just that original cube that's been sliced at that center point. All right? So, letter C, the pyramid fits inside of a prism that has the same base and a height of 1 centimeter. What fraction of the prism's volume is filled by the pyramid? Fill in the missing fraction in the equation below. All right, well, let's talk about this together. The volume of this prism, right, the volume of this prism is 2 times 1, or 4 cubic centimeters, right? 4 cubic centimeters, that's the volume of the prism, right? The volume of the pyramid, so the volume of the prism is 4 cubic centimeters. The volume of the pyramid is 4/3 cubic centimeters. So what is this compared to this? What fraction of this thing is occupied by the pyramid? Well, it may seem like 1/2. But of course, if it was 1/2, then if the volume of the prism was 4 cubic centimeters, the volume of the pyramid would be 2 cubic centimeters. In fact, think about this for a second. 4/3 is the same as 1/3 times 4, right? In which case, the volume of the pyramid is 1/3 the volume of the prism. Now, I don't really even need these calculations to really get you to be convinced about that. Remember that originally there were 6 of these pyramids that fit inside of this cube. Then I sliced the cube in half, which means technically speaking, there now must be 3 of these pyramids that can fit inside of that prism. And this is remarkable. In fact, that 1/3 relationship always holds. And what do I mean by that? Let's take a look. The volume of a pyramid or a cone is always 1/3 of that of the prism or cylinder of the same base area and height. All right? So whereas the volume of a prism or a cylinder is just base area times height, the volume of a pyramid or of a cone will be 1/3 the base area times the height. That's it. All right? And in fact, those are kind of classic formulas, right? The volume of a prism, base times height, base area times height. The volume of a pyramid, 1/3 base area times height. The volume of a cylinder, pi r squared times h. The volume of a cone, 1/3 pi r squared times h, right? So the only real difference between the volumes of pyramids, cones, compared to prisms and cylinders is an extra 1/3 factor set out front. Now this is going to be kind of tricky because my instinct at least is to think that it would be 1/2, right? Kind of like a triangle, right? The area of a parallelogram is base times height. The area of a triangle is 1/2 base times height. Here the relationship isn't 1/2, it's 1/3, all right? But we're going to use it time and time again, starting right now. Let's take a look at the Great Pyramid of Giza. This is one of the most famous pyramids in the world. The Great Pyramid of Giza in Egypt has a square base that measures 756 feet on a side and a height of 481 feet tall to the nearest million cubic feet. What is the volume of the Great Pyramid? All right, so again, it's this simple. Whether we're talking about pyramids or cones, right, the volume formula is 1/3 of its base area times its height. That's it. And then this really becomes quite a plug and chug kind of operation, right? The plain fact is the base has an area of 756 times 756, right? That's the area of the base. That's a huge number, all right? But then to make it even larger, we would have to multiply by the height, 481. All right, and then we can't forget the 1/3. Forgetting the 1/3 really would mean that we were then calculating the volume of that prism, right? But we don't want that. We've got to have the 1/3 in there, but whatever, that's easy enough, right? We could do 1/3 times 756 times 756, or times 756 squared, times 481. Oh, wow, huge. Remember, we're talking about to the nearest million cubic feet, which kind of makes sense given the kind of errors that would come up here. You'd have to look at this carefully, but think about where you'd put the commas. This is 91,636,272 cubic feet. So to the nearest million cubic feet, this would actually be 92 million. 92 million cubic feet. $92 million. That's it. All right, take a look, and we'll move on and do another one. Now, if it's not completely obvious, the only thing different about today than the last lesson is this 1/3. Ultimately speaking, we're still calculating volumes by finding a base area, multiplying it by a height, but because that constant cross-sectional area isn't there anymore, we have to multiply by 1/3. Again, why is it 1/3? To really appreciate that, you'd have to take a look at calculus. We did that first exercise, which showed it for that very, very limited particular pyramid, but at least we were able to see it, right? So let's take a look at another problem. All right, here we go. Exercise number 3. A cylinder of solid material with a radius of 4 inches and a height of 10 inches has a cone with the same radius and height removed from it. What is the volume of the remaining material? Round to the nearest cubic inch. All right, now this is a very kind of common problem. It's not too different from those shaded area problems where you had an overall area, you had to calculate, then an area that was not shaded. So you had to calculate them both and kind of subtract out the area that wasn't shaded. In this particular problem, we have an overall volume, the volume of the cylinder. We've cut a cone out and kind of thrown it away, and we want to know what the volume is that remains. All right, so again, it's a subtraction kind of process. Play around with this and see if you can get the right answer. All right, let's do it. Well, again, the overall volume is that of a cylinder, and it's got the formula pi r squared h. That's simple enough. It's going to be pi times the radius squared times the height. All right, and you could work that out. You could leave it that way. You could work it out part of the way. For instance, for me, I would do the 4 squared. That would be 16 times 10 would be 160. And then I think I'd just leave the pi there for now. Then I need the volume of the cone. Now that's actually exactly the same calculation, but just with a 1/3 out front. 1/3 pi, whoops, not pi squared. This is what happens when I try to talk and write at the same time. It just doesn't work well, which is a limitation for a teacher, let me tell you. So I've got 1/3 pi r squared h, but all of those things are basically the same. 1/3, times pi times 4 squared times 10. And not surprisingly, this is 160 pi. Now, don't get me wrong. If you, the one that's watching, right? If you think, or if you work better with decimals, for goodness sakes, work this number out as a decimal, store it, or just write out a bunch of decimal places. Work this out as a decimal, store it, or write down a bunch of decimal places, and then subtract. I'm going to do it all at once, because what I'm going to do is I'm going to calculate the volume that's remaining by simply doing 160 pi minus 160 divided by 3 pi. I'm going to do that all at once on my calculator. Easy peasy, here we go. 160 pi minus 160 divided by 3 pi. And I know that looks like it's 160 divided by 3 pi. It's not, okay? But if you're uncomfortable, you could always put parentheses around the 160 thirds and hit enter. And there it is. Now again, there's nothing wrong with working out what 160 pi is, what 160 divided by 3 pi is, and then doing the subtraction, all right? I wanted to do it all at once. To me, it's cleaner that way. 335, I believe we needed to just round it to the nearest whole number. Yep, round to the nearest cubic inch, 335 cubic inches. That's it. Check the answer board, is that right? Yep. Okay, looks good. So, view, back to the full screen. 335 cubic inches. Take a look, then we'll move on to another problem. All right, let's do it. Okay, last problem of the lesson. Exercise number 4. A pyramid is constructed from a cube as shown below. Point C is at the midpoint of edge AB. If the cube has a volume of 216 cubic centimeters, then what is the volume of the pyramid? All right. Well, let's kind of think about this a little bit backwards, kind of working our way backwards, right? We need the volume of the pyramid. That is going to be 1/3 of its base area times its height. All right? And I don't know either one of those. I've got to figure out the height of this pyramid, and I've also got to figure out the area of that triangle that serves as its base. Cavalieri's principle says it's completely okay that it's not one where the apex is directly over the center. That's fine. So what I'd like you to do is spend a little time and see how somehow using that you can figure out the correct answer. All right. Well, the key here is that we can figure out how large the side length of the square is. In fact, if this is, let's say, x, and this is x, and this is x, then what we know, right, is we know that x to the third must be equal to 216, right? In other words, that's why we call it cubing, right? That's x cubed equals 216. So if we want to know what x is, we simply have to find the cubed root of 216, which happens to be 6. In other words, this cube is 6 centimeters on each side. In fact, let me just kind of get rid of all of that. This is 6. This is 6. And this is 6. Now, one thing that's nice about that is we now know what the height of our pyramid is. It's 6 centimeters. All right? We now have to find the base area of our pyramid. So let's think about what that base shape is. Well, it's a triangle, right? Actually, let me draw the triangle. Right? So this is my B, if you will, my base, right? And what do I know about it? Well, this has got to be 6 centimeters. Right? Because it's this dimension here, right? This has got to be 3 centimeters, right? Because they told me that point C was at the midpoint of side AB, so it's got to be 3 centimeters. And we also know it's a right triangle, which is awesome, because that means I can now figure out what the base area is by simply doing 1/2 of 3 times 6, and that's 9 square centimeters. That is the area of my base. And now I've got everything I need. I know the height is 6. I know the area of the base is 9. So my volume now will be 1/3 times 9 times 6. And we could do that all on our calculator or in our heads. Either way, we get 18 cubic centimeters. No rounding needed. That's it. Let me step back, take a look, write down anything you need to, and then we'll wrap it up. All right, let's do it. So today what we did is we looked at how to calculate the volume, the amount of three-dimensional space that fits inside of both a pyramid and a cone. And it was very, very similar to the volume of prisms and cylinders, with one exception. Instead of simply doing the base area times the height, we now do 1/3 of the base area times the height. But that's it. That's the big difference, is that 1/3 factor out front. Besides that, it then allows us to calculate the volumes of many, many more shapes and do more sophisticated problems. In the next lesson, we'll take a look at the last three-dimensional shape we'll be seeing in this course, which is the sphere, and its volume formula. For now, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler. Until next time, keep thinking and keep solving problems.